now. Okay, hey guys, welcome to the 2134 Crash Course. I hope we're all excited today. I'm just going to be taking you through a few topics. Yeah, okay, let's get started. Right. Here we go. Can you guys all see the screen well, and can you all hear me? Yeah. Yeah. Wait, Jackson, are we gonna have a problem with it's not showing the iPad? Wait, let me see if I can. I think I can just show it through here. This should be fine. There we go. That'll be good enough.
I'll figure that out.
Yeah, easy. But I think that should all work. You guys can all see. Yeah, no, it works. Okay, complex power. So I'm sure you guys all remember from Quad 1 power, VI, all that stuff. Well, now we have complex power. You guys are pretty familiar with it. Sometimes it can be daunting to some students, but I think that if you get the right approach and the right mindset, it's actually one of your favorite questions in any midterm, because all of it is quite straightforward. So here are our definitions. I choose to use a lot of phases, I find them very useful. We have S, which is complex power. We have anything in bold as a phasor. We have apparent power, which is the magnitude of S, and we've got power factor. But the interesting thing to note here is all of these can be figured out from S. So S is very, very useful. Another friend of yours, the power triangle. You guys should have seen this lots. Something to be careful of on exams is units for different kinds of power. So now we have three kinds of power. We've got apparent power, volt amperes. We've got average power, your old friend from Quad 1, which is in watts. And we have reactive power, Q. And be careful of your units. Especially be careful when you're given a problem. Check what the units are. And remember that VA is not the same as VAR, which is not the same as watts. All right. Leading and lagging. So when we talk about power factor, what we're talking about, of course, is how much.
On the QR code, they have access to all the slides they want to look at.
Oh yeah, my bad. Thanks, Jackson. Scan this QR code, please, and you have access to all the slides if you scan it. So it's a very good deal.
So it's an attendance form, and at the end, your prize is the slides.
Woo. And it's a lot of help to us, so it'd be great if you can do it. All right, power factor. We all know what power factor is. Power factor is how much of the power is in the average power or imaginary power, right? And we just define it. Remember, everything can come back to S. So we can get our power factor just from the angle of S cosine, right? That's our power factor. Is anybody confused about leading and lagging? So I'll do a quick overview of it. When you have your S, or your phasor diagram, whether you have a theta that's greater than 0, or a theta that's less than 0, Q greater than 0, Q less than 0, you have two different kinds of loads. One is an inductive load, it acts like an inductor. And one's a capacitive load, it acts like a capacitor. If it's greater than 0, if theta is greater than 0, you have an inductive load, and we call that lagging, right? And if theta is less than 0, we call that a leading. It doesn't mean that the actual load is an inductor or capacitor, it's just that the equivalent impedance acts like that. Let's keep going. Okay, a question. Okay, first things first, what do I note when I see a question? These are what I look at straight away, okay? First thing I'm noticing, what do they give me? They give me two equations. They give me voltage and current. Straight away, they give me both in cosines. That makes it a lot easier for me to convert it to phasor form when I want to. Here we go. And they also give me in units of volts. No volts RMS. You should be very careful. You should always check if there's an RMS or not. You'll see it later in the crash course. So first, let's figure out the power factor, okay? So first things first, let's figure out S. right? Because once we figure out S, we can figure out the power factor very easily, and I'll walk you through that. So, here we go. We know that the definition for S, right, this is a phasor, is equal to a half V I star. Notice that the half's here, right? That's because we're not in RMS units. I'm going to keep smashing this in because it's incredibly important. A lot of students lose marks because they don't notice whether the units are RMS or not. Okay, let's write our phasors. So they've given us V of t. It's got the same angular velocity, so we're good. Okay, so let's write our big V, our big phasor V. That is just going to be 300 angle 30 degrees, and I is going to be 15, and be careful of the negative, angle of negative 25 degrees. Okay, we just plug it all in. If you've got a calculator, you can do that. That should be 2250. Remember that I star is equal to the conjugate, which means you just flip the angle, and we get angle of 55 degrees. Now that we've got our angle, it's very easy for us to figure out our power factor. It's just the cosine of this. So our power factor is the cosine of angle of S. So you can write that more generally. Give me a sec. Okay. Now, I'm going to ask you guys a question. Do we know if this is a leading or a lagging power factor? It is a lagging power factor, and you can tell very easily based on this nice little thing we've given you. But yeah, so that should be, I have the calculator here. Can you get this one isn't, I can't use the one there. Thanks. Yeah, it's cosine of 55 degrees, which you can put into a calculator quite easily, I think. No? Easy peasy? All right. But does it make sense to everyone what we've done there? 0.57? Easy. And it was lagging. Very important. You lose information if you don't write lagging or leading. We don't know if it's an inductive or capacitive load otherwise. Okay, II, we'll be quick with, here we go. Average power absorbed. S, our friend, it's back. Average power can be found out very easily from S. And since we've already got S, it is the real of S. So if you've got it in your calculator, if you saved it in your calculator, hopefully you have a complex calculator, and you can just get that as P. Otherwise, there's another way, because you have power factor. You have P is equal to the magnitude of S times the power factor, right? You can see that from the triangle very easily. Cosine of theta times magnitude of S is going to be equal to P. Okay, next, maximum power transfer. Another nice question to approach in an exam. Okay, so there's a pretty straightforward formula here. Everyone remembers Thevenin. Hopefully you're familiar with it by now. We find V Thevenin, Z Thevenin, and then depending, we're asked to maximize the power of some circuit. They want us to give us, we want to give them a load that will maximize the power used, the power transfer. So if we're allowed to do any component, like if we're allowed to use inductors, resistors, and capacitors, we do something called a complex load, and we just let, so over here, we'd have some V Thevenin, we'd have some arbitrary Z Thevenin, and we would plug in this thing called ZL, right? And as it turns out, ZL is equal to Z Thevenin star, as you'll see in a second. And if they only let us use a resistor, we just say the R is equal to the magnitude of ZL. Does that make sense to everyone? Okay, I'll move on. We can do a question now. Everyone's excited? Question 6, which is asking us find the maximum average power transfer, right? That can be delivered to the circuit. First, complex value, okay? Now that I'm looking at the circuit, I'm just gonna note a few things. They're very nice. They've given us all the resistors and capacitors in and inductors in phasor values, which makes it a lot easier for us. And we also notice that they've given us peak voltage, which means it's non-RMS, which means there's usually a half involved somehow. So if you actually see over here, this is for RMS. Okay. Okay, so the first step, V-Thevenin and Z-Thevenin. All right, this should be a problem you guys have all done by now. Let's find V-Thevenin and Z-Thevenin for our circuit. So step one, find all right. That is this. This circuit can actually be done in quite an easy way. Does anybody want to guess what kind of method we use to find V-Thevenin and Z-Thevenin in this circuit? How would you do it? Divider? It's not a bad method. You could definitely use a divider. But instead, I'm going to use source transformations.
Just watch if you're covering.
Oh, yeah. Oh, can I get the laptop with the OneNote? Yeah, thanks. You find V-Thevenin and Z-Thevenin. Okay. The reason I'm going to do a source transformation is our circuit will quickly become a Z circuit. So if we look over here, right, I'm going to do this source transformation first. So let me write this down. I'm going to source transform this. Oh, yeah. I'm going to do a source transformation here, right? And then what I'm going to do is I'm going to add these two elements in parallel. And then I'm going to do an anti-source transformation. Does everyone see how that turns the entire circuit into a series circuit? Yeah. So I'll do that quickly. So I'll just deal with this part of the circuit first. So we can deal with this. So this is what we start with. We turn it into something like this. So it will be a current AC circuit. And it will have, stupid OneNote. Okay. That's 100J. This becomes minus J, because that's 100 on 100J. And then what we do is we have this resistor already here. Yeah, forget about the rest of the circuit for now. You don't need to draw the whole circuit. We'll draw it all in a bit. Then we're going to add these together. We're going to do them in parallel, which is 100J in parallel with 100. We can do all the calculations at the end. And we're going to resource transform it back into a voltage source. So what we're going to do is we're going to times that by minus J. We have the AC voltage source. Then we also have a component that has that. In parallel 100J. Right, and then we've got the rest of the circuit we have over here, 50 ohms. We have minus 25J. And then we just have our load. All right. Is anybody fussed about anything over there? Does that make sense to everyone? All right. Okay, so the next thing we're doing is we're just going to identify V-Thevenin and Z-Thevenin. In here, it's actually quite trivial. This is our Z-Thevenin, and this is our V-Thevenin. Now, I could do all the complex numbers for you, but luckily I have it all written down already. V-Thevenin is equal to minus 50 plus 50J. And Z-Thevenin is equal to 100 plus 25J. Okay, now what are we going to do? Look at our method, right? We're asked if we have maximum power transfer for a complex load. So now everything becomes fun and just plugging in numbers. So the formula we're going to use, sub into max power transfer formula. Do you guys get this on your formula sheet? Do we know if they get it?
They get to write their own formula sheet this time.
Own formula sheet. You guys were lucky. I would say definitely write this one down. Very useful. If you don't have it, you can always rederive it, but I would just write that down. Because what you can do then is you can write an eighth v Thevenin squared over r. And r in this case is just the real part of z Thevenin because we've cancelled out the imaginary part. All right, we can sub that all in, and we will get it is 5,000 on 100. If you simplify, because r is 100 and we square the magnitude here, all of this can just go in the calculator, which is equal to 50 divided by 8, which is equal to 6.25. And remember to use units. Key part. This is going to be 6.25. Can anybody tell me the units? For doing average power transfer. I'm happy to go back onto the slide. It is watts, because we're just dealing with power, normal power. So 6.25 watts. All right, I'm not going to go through the full of II because I'm just worried about our time, but I will just ask you, it's the exact same. You don't have to do any extra work. You can just let your RL, the load you plug in to the circuit they give you, is just the magnitude of Z Thevenin. You can do the funky maths to prove that, but it's a funny proof. Do it in your free time if you have that much time. Okay, power factor correction. This is if you have this in an exam, I would be very, very happy. Like, it can get stuffed up, but if you know what you're doing, it is marks on the table. So here we go. This is what we do, right? S, right? So what do we usually want, right? When we're doing a power factor question, if we have power factor equals 1, the imaginary power, which is stuff we don't want for various reasons, is 0. Usually they're not nice enough to just give you a Q equals 0 question. They'll usually say, get your power factor to 0.95, or they'll say, get your power factor to 0.8 leading or lagging or whatever. But yeah, when we have a power factor question, what we actually do physically, what we're doing physically, is we've got some box, right? We know the power factor of it, and they ask us to add a component on the side, like an electrical component, right? So usually what we add is a capacitor in parallel, right? That's what most questions involved. But it can be an inductor in parallel if they want you to increase it, but it's almost never that. But it's a very similar method regardless. We solve for S. We find a delta Q because we want to change Q by some amount to get to the new power factor. And then we solve what delta Q, what component will get us that delta Q. So it will make it much more clear if I just show you an example. Okay, what jumps out to you guys when you read this question straight away? Anything? When you read a question, you should be looking for certain things. Anything jump out? Yes, Otto, RMS. So the voltage that we're given is an RMS, which means that no longer is S half VI star. S is now just VI star. Be very careful with this. Like, you can easily make this mistake. It's definitely happened to me more than one time. It's asking us, right, in this figure, to show or working, determine the type of circuit value used when connected in parallel with the load. We'll raise the power factor to 0.95 lagging. So remember what lagging is? If we look at our S, we're going to want our S theta, right? So if we have our previous, let's pretend we have our power triangle currently, right? We can figure it out in a second, but I'm just going to show it for the sake of argument. We've got some power triangle with some S, some P, and some Q, right? That has some power factor, it has some angle, right? What we know, because they've told us it's lagging, we will never decrease Q so much that we'll go to the other side. They very specifically want us to keep S's theta positive. That make sense? All right, so I'm going to write a little diagram. One other thing, what have they told us about the current power of the system? Can anybody look at that box and tell me what they notice about the current S of the system? Sorry? What I was looking for, so I couldn't really hear you, but what I was looking for is about the units. So what are the units of the power? Yeah, so they're giving us, when they're giving us a side of the triangle, right? Because they usually give you one side of the triangle and then the angle, right? In some way, they're giving you the volt. They're giving you the S, the magnitude of S, right? The parent power, and they're also giving you the angle and which sign that angle is. Because when you just have the angle without leading or lagging, you actually don't know if it's above or below in the triangle. So let me draw. First thing I'm thinking, power triangle. Let's go. Let's find S and draw the power triangle. So 1, find S, draw power triangle. Okay. Here, this is what I'm going to draw. Here, we've got some theta. Theta is going to be equal to the cosine inverse of 0.65, because that's our current system. So that's theta, right? And we're going to have some, we know after this, because they're asking us, the power factor is currently 0.65, right? We know that we're going to want to change the power factor by some amount. We're not actually going to change the average power at all. What we're just going to change is this Q. So adding the component just kind of can move the Q up and down. In this case, we're moving it down. And what we're doing, right, is we're trying to get this theta nu. They've actually given us what theta nu is. This is the other thing they've given us in the problem, right? Theta nu is equal to cosine inverse of 0.95. Now, ain't that interesting? And what we're actually going to do is we have this, I'm going to label these just so you guys can see. We've got this Q old, right? And then as another thing, we have this Q new, right? And what we're trying to figure out what component we actually need, right, to change the power factor, is we need some delta Q. Right, so Q old equals, Q new equals Q old plus delta Q. Yeah. Now that makes sense. You can just see it adds up, right? And what we're just going to figure out is that delta Q. All right. Now, the way we figure that out is we are going to, give me a second. First things first. Yeah, I'm just getting the numbers up so I can write them down. What time is it? Okay, easy. All right. Oh, I'm just getting up the numbers. Okay, easy. Here we go. Let's figure out what Q. We know what Q old is, right? Let's figure out what Q new is. So let's find Q new. The way we're going to find Q new is we know theta new and we know P. And we know S, right? It's because S we got from here, which is 1,200 angle theta, right? That's the S we got. We know that Q nu is going to be equal to P, right? Wait, it's like this. So tan of theta nu, right, is going to be Q nu on P, and P tan theta nu is equal to Q nu. There we go. And we know that we can find P very easily because we've got S. This is the really nice thing about having S. We can say P is equal to the real of S times tan theta nu. All right. Okay. So we have P. We have Q nu. Here we go. And because we have Q nu and we have Q old, we can figure out what delta Q is. Delta Q is equal to, from this equation that we have over here, so Q old minus Q new. Right? And from that, because we have delta Q, right, we can use the next step. So delta Q is, it's over here. Okay, that's why. I don't have any of the actual values on, because, yeah.
Just write the expression.
Yeah, I'll just write the expression. Okay, delta Q is going to be J omega 1 on J omega C, and then we know omega is equal to 100 pi because of the frequency from here, right? And from that, we can figure out C, which is what we want to find out. We can ignore the J because we've got J's on both sides, right? So what we can figure out is delta Q which will give you your answer. I don't think so.
So delta Q is V squared on like S, right?
Yeah. I think it all works out.
So instead of being equal to 1 on J omega C, it's V squared divided by...
Oh yeah, sorry. Yeah. That's a really good point. V squared over Z Thevenin. Oh, Z, not Z Thevenin, Z that we're solving for. And we can solve for that Z then. And that Z will be equal to 1 over omega C, J omega C. That's how we figure it out. Okay, I'll move on to the next system. Transfer function, oh yeah? Sorry? Yeah, you can use the power triangle, yeah. Yeah, that's all fine. All right. The next thing is, this one, very easy. I might skip this one. Does anybody feel like they want me to go through this example for power? Yeah. Okay. Anybody? I'm happy to do it. Yeah. We can move on that one. Okay. Once you actually have, so I'm just going to explain the method quickly, just in case you don't know. Right? You'd find V out as some expression of something V in, and V out over V in over here would be our transfer function. Okay. We will actually do another transfer function question, simple one. And for this one, we're going to use a voltage divider. So the first thing I'm going to do for this question, right, is, so what we're going to do is plotting frequency response. So there's a really standard method for plotting frequency response, we're basically saying we have some transfer function. We kind of want to know how it works, right? We've turned our circuit into a kind of a black box, and we kind of want to understand it apart from the circuit. So what we're going to do is we're going to plot two values. Our transfer function is a complex function, so it will output a phasor. So we want to kind of see, as we change omega, as we tweak omega over time, how does the magnitude of the response change? And we also want to see the phase, and how the phase changes over time. When you do that, so when you're doing these kind of problems, you're going to find the angle of h of j omega and the magnitude. You're going to substitute at least 0, and you're going to see the tendency as it goes to infinity, and one other point at least. You can always do 2. And then you plot these on the axes. Make sure to label your axes as well as your plotted points. All right. So in this example, a good thing to plug in would be omega equals 1 over RC. You just kind of have to get some, do some problems, get some pattern recognition of what kind of things you sub in. Okay, this one. This is a pretty standard transfer function. This one, the complex impedance here, so ZC, is going to be 1 on J omega C, which is going to be minus J on omega. And then we also have the resistor, which is the same as 1 over J omega. And that's just 1. So we'll use a voltage divider. V out equals 1 on J omega, 1 on J omega, plus C is 1 in this example.
Oh, C is 1, sorry.
And that will become 1 on 1 plus J omega, like V in, and our transfer function is equal to 1 on 1 plus J omega. We can just times this. What I'm doing here is I'm just timesing the numerator and denominator by J omega. Okay, does that make sense to everyone? This equation or this one? This one? It's V out on V in. Because we figured out V out in terms of V in, right? And then the transfer function is just, in this case, because they've asked for our transfer function here as V out divided by V in. Yeah. Okay. Now we're going to do a quick thing. We're going to get the magnitude. H of J omega is equal to, we can do the magnitude. It's going to be 1 over the square root of 1 plus omega squared, because you can, in a complex number, you can take the magnitude of the numerator and magnitude of the denominator. And that's just to do with complex numbers. And for the phase, right, we have a similar thing. We can take the arctan of 1 minus, arctan of 1 minus arctan of this, which is just omega. And we can figure out that this is just minus arctan of omega. So we've got our two things. Let's plot. To plot, we are going to let's do everything our instruction says. Okay. We will plot our axes. Okay, we're going to have omega versus the magnitude of h of j omega. And we're going to have another similar one, which is going to be omega versus the angle of h of j omega. All right, so what we're going to do to actually plot these is we're going to substitute the points that we mentioned before. So we're going to do omega. We're going to do the magnitude of the transfer function and the angle of the transfer function. Okay, so what points are we going to plot? What points do you guys think will be good for plotting these? Any ideas? All right. I'm going to do 0. We mentioned we're always going to do the tendency to infinity. And we will also do one more point, which is going to be, in this case, we're going to plot omega equals 1. And you'll see why that turns out to be a good point. Okay, let's just sub it in. The magnitude is 1 on root 2. For this one, it is here, it is minus arctan of 0 is 0, so it's just 0. And for the next one, it is going to be, we plug 1 in, okay, we get, oh sorry, this is 1. This is 1 on root 2 over here for the magnitude at omega equals 1. And the angle is minus 45 degrees. And then as it approaches infinity, we know this will go to 0. As we can see, the denominator becomes increasingly large. And we know the angle will go to minus 90 degrees. So let's plot our points and then we'll draw. Okay, first thing, this is for omega equals 0. So we'll write 0, 1. Next point, it's going to be 1 on root 2. So it's around 0.707, which is going to be around here. And then we're just going to approach 0 as we go. So that'll be like an asymptote this way. So the way it will look when we connect these up is going to be like it's going to go like that. And it's going to go to 0. We do the same thing for the angle response. 0, let's make sure to line them up. It's really nice, if they ask for both, for you to line up your graphs. The examiners will like that, and it will make your information easier to read. So this is going to be minus 45 degrees, so this is 0. This is going to be minus 45. And it is then also going to go to approach this asymptote at minus 90 degrees. And we will connect the dots, and it will go like that. All right, any questions? Sorry? Yeah? Like over here? That is not correct. That is tan inverse 1 because you're taking the numerators when you have like a complex number and you take the argument of like z on omega, you're going to take the angle of z minus the angle of like w. Like if you have two complex numbers.
You are right. So it's like for the numerator and for the denominator, it's like imaginary divided by real right? Yeah.
Wait, do you mean over here?
Yeah, so for the first tan inverse, we have imaginary part of 0, and that gets divided by 1. So we have 0 divided by 1 is 0. So for that first tan inverse...
Oh, sorry, I see what you're saying. Sorry, that's completely my fault. Okay, yeah, it is 0. Yeah, that's my bad. It's a 0 on 1. Thank you. Yeah, okay. Let's move. Any questions? All right. Okay. Resonance. Okay. now this is a bit of an annoying topic, but we will get onto it. It's very mathsy a lot of the time, and you want to be very careful. So there's something called the resonance condition. So when we have a circuit, we have some input impedance and impedance that we see from the input, and the condition, and when the imaginary part, when we change omega, if we imagine having different omegas for our input impedance, when x goes to 0, we call that the resonance condition. There's a few special things about resonance. We'll go onto them. Okay, this is series resonance. It's the basic maths. You've all seen omega naught equals 1 on square root of LC before. And we also know that when we hit resonance, we get a maximum power. So we get the maximum power use, which you can see over here. Parallel is very similar. With this parallel problem, instead of using impedances, we use admittances, but the maths lines up the same. And over here, yeah, it's almost the exact same. We can see over here, this is kind of like if we tweak little omegas as we into our input circuit, we expect different responses. This is showing current, but that's proportional to power, so you get similar things for each of them. But this is kind of what it looks like. We have the lower cutoff frequency, the upper cutoff frequency, and the bandwidth. Now, you guys have heard of Q factor before? Okay, we define Q factor, which I think will just be down here. So yeah, so we've got the half power frequencies are defined as the points when we tweak the omega, half the power is used as at the maximum point. We have, yeah, that's our definition of bandwidth. It's just this. Yeah, so we've defined Q factor. That kind of tells us how pointy the graph looks. So if we have if we have a very small bandwidth, right, we're gonna have a very large Q factor. So this is a very small bandwidth, so we're gonna get it like that. Or we can get ones with smaller Q factors that look more like that, right? So this would be a small Q factor, and this would be a large Q factor. Now there's an important thing to note about Q factor, which is the Q factor approximation. Now, this is a really nice approximation when you're working on the problem, when you can just figure out bandwidth from Q factor and then use that to figure out the lower and upper cutoff frequencies. But if Q is greater than, but if Q is less than 10, we can't do that because the curve is not symmetric enough. Okay, this will be the last problem I take you guys through. So let me show you how this one works. So you guys know the standard method of finding upper and lower cutoff frequencies, right? If Q is greater than 10. Yeah? We're going to do one where Q is less than 10. So that sounds like a lot of fun. Okay. Okay. Now, let's go through this problem. A part I. Okay. First part. Derive and calculate resonant frequency. Okay. Remember our resonant condition. That is the imaginary impedance input is equal to 0. Right? And when we do that, we can figure out in this circuit what Z in is. Z in is equal to R plus J. It's going to be omega L minus 1 on omega C. Okay? And when we solve the imaginary, which is this part, equal to 0, we obtain omega L minus 1 on omega C is equal to 0. When we solve that, omega squared is equal to 1 on LC, and omega naught, which we call the resonant frequency, is 1 on square root of LC. Yeah? Okay. II. What's the next part? Now this is the part that you have to be a little careful of. Like I mentioned, Q factor is less than 10 in this question. It says calculate the half power frequencies and bandwidth. the way we're going to do this, right, is a bit different than this. This is what you're mainly going to do if Q is greater than 10. But if Q is less than 10, and something that they don't tell you and they try to trick you, you have to actually manually figure out the half power frequencies. So recall what the upper and lower half power frequencies are defined as. They're equal to half the power max. So what we have over here is we want to figure out what omegas get us to this half of power max. To do that, let's find power max. Okay, everyone remember how to do the power max? To figure out the power max in this case, all we need to do is plug in the resonant frequency and see what the power is, right? In this, there's actually a nice thing here, right? Because at resonance, you know that the impedance, right, the imaginary impedance is equal to 0. We only really need to consider the voltage, which doesn't change, and the resistance. So we've got the voltage, we've got the resistance, we can figure out what the power max is. Let's check. Did they give it to us in RMS? No, they didn't. So we have to use this formula, which is always be careful of whether or not they're giving you RMS or non-RMS units. Okay, so R is 200. VM is 20. So we're going to get 20 squared divided by a half divided by 200, which is going to be equal to 400 divided by 400. How nice. Let's hope the exam has answers that are that nice. Okay, so we know what power max is. It's just 1. Now we're going to solve this. Now, the way we're going to do this, right, is we are going to write an expression for power first. We're not going to be able to, in terms of omega, because we have to solve for our omegas. So the way we're going to do this is we're going to know power is equal to, like we said before, the voltage squared. And instead, we're going to divide by whatever the input impedance is, right? Divide by 2, because we have, like I said, I keep repeating myself, non-RMS units. Okay, let's write down this input impedance. So Zin is equal to R, and remember it's equal to R plus J, and we're going to have omega L minus 1 on omega C, as we calculated in the first part of this question. The next thing we're going to do is we're going to take the conjugate. This is just what falls out of the power formula. So we're going to get R plus J, 1 on omega C minus 1 on omega L. And, minus omega L. And what we're going to do is then find what is the magnitude of this and plug it into here, and we'll get it worked out. So the magnitude of this is going to be equal to, it's going to be this squared, the square root of this squared plus this squared, right? And we can now plug it all into here, over here, okay? Let's take it back and let us do our calculations. So what was our, so we're going to get VM squared is 400, because it's just 20 squared. We're going to divide by 2, and we're going to get the magnitude of here, which we've written out for ourselves. Here we go. R squared plus 1 on omega C minus omega L squared. And what is it going to be equal to? What are we actually solving for? We're solving for P omega is equal to half the max power. And nicely enough for this problem, this just goes to 1. So we're just solving for P of omega equals a half. So let's solve that. We're going to get a half equals 400 on 2 square root of r squared plus 1 on omega c minus omega L all squared. And then we are going to solve. We're going to do some nice little algebra. We can square both sides, times both sides by 2, and times the denominator to this side, and we get r squared 1 on omega c minus omega L all squared is equal to 400 squared. Is everyone happy with that so far? Okay. Then we get 1 on omega c minus omega L all squared equals 400 squared minus r squared. We can plus minus square root both sides. And we end up with 1 on omega c minus omega L is equal to that. Let's times the entire expression by omega. So we get plus minus omega square root of 400 squared minus r squared is equal to 1 on c minus omega squared L. Let's write it out in a nicer way. So we have the coefficients. You might be scared right now because what you see is something you usually don't see. Even before we get the quadratic, we've got a plus minus. You don't have to worry in this example, it actually sorts us out quite nicely and will lead up to that. So let me write the actual values in. Here we go. We end up with, if we apply the quadratic formula, this is our A, this is our B, including the plus minus, and this is our C. So everyone remembers the quadratic formula, negative B plus or minus square root B squared, all that should be in your head by now. So we're going to end up with minus plus square root of 400 squared minus r squared plus or minus the square root of 400 squared minus 200 squared plus 4L on C all over 2L, because that's it. And that's our omega. Now what I'm just going to do is I'm going to plug in the values and figure out roughly what these numbers are. So we don't have a calculator on me, but we know this is 200. We know L on C is over here, 10 times 10 to the negative 3 over 10 times 10 to the negative 9, which should just be 10 to the 6 if I'm not mistaken. And from this, we can figure out that this is roughly 400. You can do the exact numbers when you're doing your calculations. This is roughly 2,000, and we're dividing by 2L, and L is just, so it'll be 20, and this is all times 10 to the 3. All right, why do the pluses and minus sort themselves out? We are forced to take this as a positive. We can't have a negative frequency. So we can just write this as a plus now. And what we end up getting is we get roughly 1,600 on 20 times 10 to the 3 as one of our things, and we get 2,400 on 20 times 10 to the 23 times 10 to the 3 as the other one. So this is going to be our omega lower, this is going to be our omega upper, and we figure out that if we take omega upper minus omega lower, that's going to be our bandwidth, right? We get, if you do all the maths right, is we get 34.6 times 10 to the 3. And if you remember what our definition of Q is, Q is just omega naught divided by our bandwidth. If you remember, omega naught was 100, so it's 100 divided by 100,000. So times 34.6 times 10 to the 3, which is going to end up with our Q factor being 2.87. Am I out of time now?
No, you're good.
Okay. There's just
Probably not enough time for the next example.
no. Oh, I think we're done.
Hold on.
Is there? Are there? I think this is out of battery. Okay. Are there any questions? Yeah. So are you sorry? Are you saying that we can? Why can we use it? Oh, yeah, you can use v over square root 2, or you can use the power on 2. And the reason is for our definition of power. So if you remember what our definition of power is in terms of v, right? It was v Thevenin squared, right, over 2 z star, right? Now, if you notice, if we're trying to find half power frequencies, not v Thevenin, sorry, just v. This is our formula for power, for complex power. It's like that, right? So you're asking, it makes sense to you why we can use half power, right? The v. The transfer function?
Yep, so that's the same because say you have your transfer function as a function of voltage, the square of that transfer function will be proportional to power, right? So if you're doing in terms of transfer function, then that will be over square root of 2 instead of over 2 because you need the square root of the power to get back to your
Yeah.
voltage transfer. So that method also works.
Well,
More convenient.
Which one? Transfer function or the power?
Yeah.
It is. Typically more convenient just because you end up needing to make the vanity spectrum of your transfer function anyways. So you already have that information.
you can see why, in a specific case here, if we set up this, we will obtain that the v half equals v max divided by square root of 2. It comes directly from this equation because of the proportionality. I think you asked a more general, but that's the specific case.
Cool. Can we give Josh a big round of applause?
Thank you, guys.
Yeah, this one's out of battery. Can you guys hear me at the back all right? Okay. Cool. All right, so quick introduction. Hi everyone, I'm Jackson, Academics Director at ELSOC and also one of your lab demonstrators for this course. I'll be taking you through the 3 later topics that will be assessed in your midterm. So Fourier series, I hope, is relatively familiar to you guys. I'll be spending much more time on Fourier transform and magnetically coupled circuits. So got 55 minutes, hopefully we can get through it all. So let's start with definition of a Fourier series. So you would have covered in your lab, the whole point of Fourier series is when we have a periodic function that isn't particularly sinusoidal. Say, for example, we have a square wave. We might want to decompose that into a sum of infinite sum of sine waves. And the benefit of that is we can apply phasor analysis to sine waves. So if we look at the definition, A0 is our DC offset term, and then our AN and our BN coefficients correspond to the magnitude of each of the harmonics that we have. And we can see that this can all be calculated with these formula. One important thing to note is finding the fundamental frequency, which we do through this equation, which is omega naught equals 2 pi on t. And when can slash should we use Fourier series, we should use it when we have periodic signals that are non-sinusoidal. Great. Some other forms of applying the Fourier series. I understand that your lecturer would have gone through the exponential version in quite a lot of detail. One important thing to note is that these are simply different ways of expressing these infinite sum of sinusoids. They don't give you different answers. So using either of these forms in your midterm exam, you won't lose any marks for choosing trigonometric over exponential or vice versa. And then the least popular form would be the amplitude phase form, which we have at the top here. A big tip for your exam, usually if your lecturer is nice to you, they will pick a waveform that has some level of symmetry. And when we have symmetry in a waveform, we are able to simplify our calculations by immediately knowing that some of these values are 0. So for example, let's start by first determining the different types of symmetries. So even symmetry is the simplest one. It's simply a reflection of the left side onto the right side along the y-axis. Odd symmetry and half-wave symmetry are a bit more difficult to distinguish. So the way that I like to distinguish between odd and half-wave symmetry is I will look from the origin of both. With odd symmetry, if I move in one direction towards the right, then when I move towards the left, they should always be moving in exactly opposite directions. So if this one moves up to the top right, then this one will move down to the bottom left. And as this one moves down, this one moves up, and you can keep repeating this. They will always move in opposite directions. But with half wave, that is not true. For example, if I'm moving towards the right, I go up by 2 and to the left by 1, to the right by 1. If I move towards the left, I go down by 1 and to the left by 1. So this is clearly not odd symmetry because it doesn't have that exact opposite correlation. Cool. So let's try applying that to a question. Consider the function it shown in figure 4, where a is 2 and t is 8. Showing all working, determine the trigonometric Fourier series. So can anyone tell me what symmetry we have for this function? Odd? Yeah, odd. So if I, again, start from here, and I look towards the right and towards the left, they are always moving in opposite directions. So this is odd. So to do my calculation, immediately I'm jumping up to these symmetry conditions. And for odd symmetry, we know that A0 and AN are both 0. So I'm going to note that. A0 and AN are both 0. To calculate BN, we have the option of using this formula here or this formula here. They're the exact same thing, but for your midterm, you probably want to be using this formula here. So slightly quicker because we only need to integrate over half the period. So let's apply that. So we have Bn equals 4 on t, integral from t on 2 to 0 of f of t sine n omega naught t dt. So if I look at half of this period, I'm going from 0 until here. If t is 8, then half of this period will be 4. So I can see that I have a peak at amplitude A for 2 seconds, and then a amplitude of 0 for another 2 seconds. So if I was to write that, I would have 4 over t, which is 8. And then we have the integral. So I will do the amplitude of 2 first. So amplitude of 2 is between 2 and 0. F of t is just the DC value. And then we have sine n, and we need to times this by omega naught. So if we recall, our fundamental frequency is found by this formula here. If our period is 8, then this will simply be pi over 4. So I'll sub that in. Then we have the same for between 4 and 2. We simply have 0 times the same thing. Integral of 0 will just give us nothing. So really, we only have to worry about this first part here. Great. If I take this 2 out to the front, then I will have 8 over 8, which is just 1. And then I have the integral from 2 to 0 of sine n pi on 4t dt. Integral of sine is negative cos, so this is negative. Derivative of the argument is n pi on 4, so taking the reciprocal of that, we have 4 on n pi, cos n pi on 4t. Great, and this is between the boundaries of 2 and 0. If I sub those in, we have minus 4 on n pi, cos of, so we're subbing in for t, so we have n pi on 2, and subbing in 0, we just get cos of 0, which is 1, so minus 1. So in the final form, our answer for Bn will be 1 minus cos of n pi on 2. Does anyone have any questions about how I found Bn? Chill? All right. So to write the final answer, we have the sum from n equals 1 to infinity of 4 over n pi, 1 minus cos n pi on 2 times sine n pi on 4t. Great. So going back to the whole point of why we're doing Fourier series, the whole point is so that when we get a non-sinusoidal signal, we can convert that into a sum of sinusoids as we've done here, and we can apply that to a circuit. So let's jump into this question. Let's do B for starters. So B is asking, sketch the amplitude spectrum of I of t from part A up to the 5th harmonic. So all I have to do is taking this equation, I'm equating, is Josh here? I think this is frozen. Yeah.
Interesting. Oh,
Is that it?
probably is. Yes.
Oh, okay. Thanks. Great. Sorry about that. So let's continue. So to first find the first 5 harmonics, I'm going to find n, 1, 2, 3, 4, and 5. So for n equals 1, I have 4 on pi, which comes from this term here. Then I have 1 minus cos of n pi on 2, n is 1. Cos of pi on 2 is 0. So this is 1 minus 0, which is just 1. And then I have sine of pi on 4t. And I'll repeat that for the other ones. I won't bore you with the exact math. So this should be 2. This will be the fourth one is important to note that when we sub in n equals 4 here, 4 times pi on 2 will give us 2 pi. Cos of 2 pi is 1, 1 minus 1 is just 0. So this is entirely 0, but the frequency we're meant to have here is omega equals pi. And for the last one, we have 4 on 5 pi times 1 sine of 5 pi on 4t. Great. So if I were to sketch the amplitude spectrum, spectrum are always in terms of frequency, and the magnitude of this would have peaks at each harmonic. For example, as we see in LT Spice in our labs, when we take the FFT, we see these peaks for each harmonic. This is the exact same thing that's happening here. So we have a peak at pi on 4, pi on 2, so on, until 5 pi on 4. And all we have to do is we take the amplitude at each of those harmonics. So the first harmonic will have an amplitude of 4 on pi. Second harmonic will have also an amplitude of 4 on pi, as those 2's cancel out. 3 will have an amplitude of 4 on 3 pi. The fourth harmonic will have amplitude of 0, and the fifth will have an amplitude of 4 on 5 pi. Is everyone happy with that? Great, I'll move on. So going back to the circuit, now we are asked to find the voltage Vt in the circuit shown using only up to the third harmonic. So if I was going to apply what we've done in Fourier series, first thing I need to do is I need to convert this to the frequency domain. As we've learned earlier, Z of C will be 1 on j omega C. To find this voltage, this is simply the voltage across two parallel impedances, so I can just use Ohm's law. So this will be V of t, sorry, we're not in time domain anymore. This is a phasor. So this is V equals I times 10 parallel 1 on j omega C, C is 2, so this is 1 on j to omega. And that will be I, this will be 10 on j to omega, 10 plus 1 on j to omega. I'll times everything by j to omega to get rid of these ugly fractions. So we have 10 over 1 plus j 20 omega. Cool. So this is the expression that I'm going to be using to find the voltage for each harmonic. It's important to note that I haven't subbed in a value for omega, and that's because at each harmonic we're actually dealing with a different frequency. So I need to keep that omega there. So continuing on, we need to consider n for 1, 2, and 3. So for n equals 1, V will be looking at this one. Oof. This will be 4 on pi. Because we're converting to the frequency domain, that sign, I like to turn these signs into causes just as convention, so that will have a phase shift of minus 90. So I'll represent that as minus 90. And then I need to multiply that by this parallel impedance here. So this, I need to sub in omega, which for the fundamental frequency is pi on 4. This is 10 on 10 plus j 20 times pi on 4. And I would repeat that for the other ones. For example, for the last one, we have 4 on 3 pi, angle of minus 90, and this will be 10, 1 plus j 20, 3 pi on 4. So I'll provide the answers, the numerical answers. So if we chuck this in our calculator, what we would get is 0.81 with an angle of minus 176.36. 2 would be 0.405 with an angle of minus 177.96. And our third harmonic will have an amplitude of minus 178.78. Great. Does anyone have any questions on Fourier series before we move on? Cool. All right. So the topic I'd like to tackle next is Fourier transform, and that's because it's like the older brother of Fourier series. The main difference between Fourier series and Fourier transform is that Fourier transform converts your function directly into the frequency domain, whereas Fourier series, as we mentioned earlier, it converts it into a sum of signs in the time domain. So these are the definitions for the Fourier transform. If we want to convert a function in the time domain directly to the frequency domain, I'm going to use this definition here, which is the definition of the Fourier transform. If I have a function in the frequency domain and I want to convert that back into the time domain, I'm going to use this formula, which is the inverse Fourier transform. Now, when would we want to apply Fourier transform to a signal? We would want to apply this when we have an input that is non-periodic. So say I get an input to my circuit which is just a pulse. Because this doesn't have a period, we can't find the fundamental frequency and we can't apply Fourier series. So in this case, we have to use Fourier transform. So we apply Fourier series when we have non-periodic signals. Great. So when we do Fourier transform, we'll come across two very important functions. The first one is the Dirac delta function. Dirac delta is defined as being 0 everywhere except when t equals 0. At t equals 0, the height of it is undefined. The way I might explain how this function comes about is through this condition, which is that the area under this undefined impulse is 1. So you can imagine if I have a rectangle with an area of 1, and I keep shrinking the bounds inward and inward, like so, while maintaining an area of 1, eventually I will just get a singular peak at the origin with boundaries that are infinitesimally small. So this is what we call our Dirac delta function, or our unit impulse function. Unity step function is another important one that we use a lot in Fourier transform, because typically we define our inputs as existing only for t greater than 0. So our unit step function is simply 0 for all t less than 0, and it just jumps up to 1 at t equals 0. So this is our step function. Transform pairs and properties. These will be your best friends when you are doing your midterm exam. Rather than having to apply this giant massive integral every single time, what we've been provided for Fourier transform is a bunch of pairs where we've already been given the pairs to correlate the time domain function directly to the frequency domain. And these are very useful to save you time in your midterm. Another thing we've been provided with is properties of Fourier transform. I'll mark the most important ones that I believe are important. So the first one is linearity. That's important when we want to be breaking apart our functions and converting them separately. Scaling, time shifts, frequency shifts, and we'll be seeing an example where we use these differentiation properties as well. Those are very important. The last one that your lecturer might not have focused too much on is something called the sampling property. Sampling property is very, very useful as a shortcut. So we can see that with sampling property, we have when a function of time is multiplied by the impulse function at some time t0, the result of this integral is simply the function when we sub in that time value. So we'll see in this question that's coming up now how that's used. So let's jump into our first question. If f of t is delta t minus 1 plus delta t plus 1, derive f of omega using the definition of the Fourier transform. So let's jump up to the definition. This is the definition we'll be using. So I'll write that down. So we have the integral from infinity to negative infinity of our function multiplied by e to the negative j omega t dt. Great, I've copied that correct. So the first thing I'm going to do is I'm going to break this apart into two separate integrals. Just so it looks a bit clearer when we apply sampling property. So now this is in the exact form of the sampling property formula that we have here. So our function, in this case f of t, is our e to the negative j omega, and the time that we're sampling at is 1. So the result of this function is just e to the negative j omega t, when we have t equals 1. So this is just e to the negative j omega. Similarly, this will be e to the j omega. And if I want to simplify that, I can use Euler. So if I factor out a 2, then I know this will become like so. And do we remember what this is as a trigonometric function? Cos, yeah, cos. So this will be 2 of cos omega, which is our final answer. Alright, let's do a bit of a harder example. Determine the signal f of t whose Fourier transform f of omega is shown in figure 7. So always with these types of questions, there's multiple ways of doing them. I'll give you some examples of different ways that we could solve this question. So one method is probably a bit more intuitive. Rather than doing 3 different integrals of this level, and this level, I might break up this into a sum of 2 different frequency responses. So this might be between -2 and 2 with a magnitude of 10. And I'm adding this to another frequency response, which is between -1 and 1 with an amplitude of 10. Do we see how if I add those 2 together, we'll get the waveform that we originally have? Yeah? So that's one method, and I would take the definition of the Fourier transform, or inverse Fourier transform for each of them. Another method, which might be a bit quicker, is to apply one of our properties of the Fourier transform. The great thing with when we have square wave functions is when we take the derivative, so we're in the frequency domain, so we're going to use this property. When we take the derivative, these flat parts have a rate of change of 0. So they will have basically 0 frequency, 0 amplitude. So if I draw the derivative of f of omega, the only frequencies where there's a change in the rate is here at -2, here at -1, here at 1, and here at 2. So if I was going to draw the graph of the derivative, this would look something like this. And these would have an amplitude of however much the frequency changed. And this would be at delta of t plus 2, so on. This would be delta of t minus 2. And this would be delta of t minus 1, delta of t plus 1. Is everyone happy with how I did that? Yeah. I understand this is quite new, because Sethu only really went through Fourier transform today, So yeah, if I'm going too fast, or if you have any questions, please put your hand up and I'll try my best to explain. So let's try solving for f of t using one of these methods. I might use method 2, just because in this case it will be a bit quicker. So for method 2, we have the derivative is equal to, all of these have an amplitude of 10, and we have 4 impulses, which I'll just write here. So I need to take the Fourier transform of this, inverse Fourier transform, sorry. So if we jump to our definition of the inverse Fourier transform, we could apply this integral to get the answer and use sampling property. Or another way we might do it is simply using the Fourier transform pairs, which we haven't done yet. So I might do it this way. So I can see that if I write this slightly differently, if I divide everything here by pi, I can factor in a pi here, and I will have, these are meant to be negative because they have negative amplitude. So for the t minus 2 and t minus 1, these will have negative signs out the front. So I will write that. So I have positive t plus 2 minus t minus 2. And then we have the same for t is 1. So I have something like this. If I look at the transform table, I see that this this sign is very similar to j pi delta omega plus omega naught minus delta omega minus omega naught. So I'm going to use this Fourier transform pair. So I'll write that down. So we have sine of omega naught t equals j pi delta omega plus omega naught minus delta omega minus omega naught. So we're going to use this formula. So I need a j out the front. So if I was to chuck a j out front, I would need to factor out a j on the denominator. And then I can just sub in the formula. So I have 10 on j pi. This would all become sine of 2t. And the second term will just become sine of t. Is everyone happy with that? Cool? Okay. So this is f of, so this is the Fourier transform of the derivative of f of omega. So if I was to find the Fourier transform of f of omega, I would need to use this property. So since we have the derivative of f of omega, this is equivalent to t times f of t. So I'm going to sub that in. So this is f derivative of f omega, which is t f of t. So then I have f of t is 10 on j pi t sine of 2t plus sine of t. This is looking a bit ugly, so I might convert this, to sinc. So if you haven't seen sinc before, the definition of sinc is sine of alpha over alpha. So to convert that, I would need a sine of 2t over 2t. So I would need to multiply that by 20 on, I've made a mistake. What have I done? So there is not meant to be a j here. Where have I gone wrong? We might have to come back to this if we have time. So yeah, sorry, this is meant to be 20 over pi, and this is meant to be 10 over pi, sine of t on t, and this is giving me 20 over pi sinc of 2t plus 10 over pi sinc of t. Great. So yeah, mistake somewhere. I'll come back to it if it pops to my head. In the interest of time, I might have to skip amplitude modulation. If we have time, we'll come back to it. It's not a major point for Fourier transform. I really want to get onto magnetically coupled circuits. So magnetically coupled circuits are a bit hard to understand in the beginning, but once we get this thing called the dot convention, all it really is just applying a bunch of KVL equations. So going into the dot convention. The whole reason we have dot convention is because we have two coils that physically are placed quite close to each other. And what happens when we have two coils or inductors close to each other, the flux through one coil might be linking with the flux through the other coil, which gives us what we call our mutual inductance. And this mutual inductance has an impact on our KVL equations through these terms here. So to apply dot convention, what I will look at first is the direction of current in each of the coils. So I1 is flowing this way. The important thing to note is I1 is flowing into the dotted terminal. So then the other dotted terminal on this side will be positive and the other end will be negative. Similarly, in the second coil, I2 flows into the positive terminal. So the positive terminal will be at the dotted terminal on my first coil. And that is how we figure out the polarity of the impact of mutual inductance in both coils. In my second example, instead, I have current flowing into the dotted terminal again. So this will be positive, and this side will be negative. But now current I2 is flowing in the opposite direction. So I2 is flowing into the non-dotted terminal, which means this dotted terminal will be negative, and this one will be positive. The reason this matters is because now, when we look at the direction of the current here is flowing into the negative terminal of the mutual inductance. That means that the contribution of the mutual inductance will have a negative voltage. And that will occur for both of our meshes. Whereas in the first one, we have the current flowing into the positive terminal of our mutual inductance, which is why these mutual inductances will have a positive voltage effect. Does everyone understand dot convention? Cool. All right, we'll do a couple examples later on. For when circuits get a bit more complicated, I like to apply the equivalent model. So again, just quickly, to find the polarity of the mutual inductance, we'll follow the current through, hits the dotted terminal. So this dotted terminal will be positive, negative. Current I2 flows into this negative terminal, so this one will be negative, positive. If I don't want to worry about dot convention while I'm doing my KVL equations, I can convert this into dependent voltage sources. So all I have to do is to take the polarity of the mutual inductances and convert those directly into dependent voltage sources. And these voltage sources will have a value of our mutual inductance times I2. Because if we really think about it, this is just the impedance of our mutual inductance times the current, which will give us a value for voltage. Cool. Let's jump into a question. First question is asking us to find the load current IL, which is the same as current I2. So to find this, first thing I always do is dot convention. So current I1 flows into the dotted terminal. So will the dotted terminal on the other side be positive or negative? Positive. So this will be positive and this side will be negative. I2 flows into the non-dotted terminal. So will this dotted terminal be positive or negative? Negative, yeah. Once I've done that, I can write my KVL equations. So my first KVL equation will be for I1. If I follow I1, flows into the negative terminal of this voltage source. Then I have all of these impedances. So 8 ohms minus J 12.4 ohms and J 12 ohms. So I will combine all of those. And this is all multiplied by I1. And the last thing to consider is the mutual inductance. So in this case, our mutual inductance has a value of J10. If I scroll up, since this is flowing into the negative terminal of our mutual inductance, this will have a value of minus J omega M I2. So this will be minus J omega M I2, and J omega M in this case is just J10. So this is just minus J10 I2. So it's really important to note that the mutual inductance will be linked to the current in the other coil. even though we're doing a mesh or a KVL equation for the first mesh. Then we have KVL2. So in the second mesh, I have an impedance J15 and 20. So this will be all multiplied by I2. And then I have to consider the mutual inductance again, which will be minus J10 I1 equals 0. If I want to solve for the load current, or in other words, IL, I might want to sub out I1 in our first equation. So to get an expression for I1, I'll use the second mesh, and this will give us a value of 20 plus J15 over J10. And if I sub that into my original equation, I will get a massive expression. So this is plus 8 plus minus 12.4 plus 12 is minus 0.4. So this is minus J 0.4 I1. I1 will actually sub in as the value that we just calculated, which is 20 plus J15 J10 I2 minus J10 I2. And if I rearrange this whole equation to find I2, I would be getting 100 over 8 minus J 0.4, 20 plus J15 over J10 minus J10. And that gives us a value of 3.46 with an angle of 67.2 degrees. Any questions about magnetically coupled circuits? Chill? Okay. The second part is finding the average power absorbed by the load, 20 ohms. So to quickly do this, as covered by Josh, to find the power, that is just the peak value of the current. Oh, sorry. We're going to be using, no, my bad. We're using current. We found current. So this will be half the peak value of the current squared times our resistance in the second mesh. So this is going to be IL, because that's the current flowing in the second mesh, which had a peak value of 3.64. So this is going to be half 3.46 times 20, which will be roughly 120 watts. Done. Some other things that might come up in magnetically coupled circuits. First one is instantaneous energy. So if I wanted to do a question on this, it's important to note that these inductances are in henries. So if I was using this circuit, I would need to convert these inductances back into, these impedances back into inductances using something like this. And then I would just sub in my value for time into these equations for the current that we've calculated. Coils in series, a bit of a rarer question to come up, but if we have a current that flows into the dotted terminal of both coils, then we will have a positive impact of mutual inductance. And if the current flows into the dotted terminal of one, but the non-dotted terminal of the other, then this mutual inductance will actually have a negative impact. Last thing to note is the coefficient of coupling. So coupling tells us how much of the flux from the first coil is going through our second coil. So you might like to think, if all of the flux in the first coil is being linked to the second coil, then we have a coupling coefficient of 1. If instead we have none of the flux from the first coil going into the second coil, then we have a coupling coefficient of 0. And we calculate that coupling coefficient just through this formula here. So we have 15 minutes, so I'll try to get both of these examples done. First one is asking us to find the total instantaneous energy dissipated by the magnetically coupled coils. So I'm going to be using this equation here. Oh, this one? Oh yeah, sorry, that's a good point. So that correlates directly to whether we're adding or subtracting our mutual inductance. So if when I do my KVL equation, I'm adding, then it will be the same for the instantaneous energy. It will be adding. So for the example that we just did, for example, we had the mutual inductance was subtracting here. So then this will be using the negative term. So I'll apply that in this question. So things I need to find: L1, L2, I1 of t, and I2 of t. So let's start with L1, L2, and M as well. So these are all inductances. So M. If I'm going to convert an impedance back to an inductance, I just need to do the impedance divided by omega. So L1 will be this value here, L2 will be this value here, and M will be this value here. So I have L1 is 12 over omega. Omega is 2 pi times the frequency, which is 100 pi. And I'll repeat this for the other ones. So that's all of our inductances. Next, I will need to find I1 at our time, which is 0.2. That will be a value of 3.904. If you want to validate your value for I2, it would just be subbing it into this equation here. And that will give us a value of 8.66 with an angle of 14 degrees. Great. So once I've found my values for the currents, I can then sub it into the equation. One important thing I might note is to actually calculate these values, to sub in time equals 0.2, I would first need to convert this back to the time domain, which would be sine. Is it sine? No. Let's assume it's cos in this question. So cos 100 pi t plus 14 degrees. And I would sub in t as 0.2. But the important thing is, this is in degrees. So before I sub in anything, I need to make sure that this is pi on multiplied by pi on 180. And that would give us our value that we have down here. If I sub in all the values, then my last answer will be omega, or the energy at 0.2 is 0.1575 joules. And then the coefficient of coupling is just using all of these, and this is m over root L1 L2, which is 0.745. Cool. All right, last 10 minutes, let's do quite a challenging magnetically coupled circuits question. So the reason this is so challenging is because I have a coil here that's magnetically coupled, but it's also right in between two meshes. So this is going to get quite complicated. First thing I always do though is I try to apply dot convention. So let's start with the easier coil, which is this one here. So the current is flowing into the dotted terminal. So this dotted terminal will be positive and negative. The issue comes when we're trying to find the current flowing through this middle coil. How do we know if the current is flowing from the top to the bottom or from the bottom to the top? Because we have a current I2 and a current I1 interacting with that coil at the same time. So to solve this question, I need to make an assumption. I need to assume that either I1 is greater than I2 or I2 is greater than I1. In this case, I'm going to say that I1 is greater than I2. So that means that the current will have a net direction in the, from positive voltage to negative voltage, and this current will be I1 minus I2. So I look at this current, this net current, and I think, does this go into the positive or the negative, into the dotted or the non-dotted terminal? It goes into the non-dotted terminal. Yep. Assume the direction of I2 is this way. You can, but in this case it's explicitly stated in the question, the I2. But if it's not defined, feel free to do that. The only difference in your answer will be if it actually was going the other way, you would just get a negative current, which tells you it was actually going the other way. So, as I was saying, this current flows into the non-dotted terminal, so this will have a negative polarity at this dotted terminal and a positive polarity here. This is getting quite complicated already, so I'm going to apply the equivalent model this time. So I'm going to add in my dependent sources. So I just look at the polarity of the mutual inductance, which will be like so, and these will have a value of 3J times the current of the other coil. So for this coil here, the other current is I1 minus I2, so this is J3 I1 minus I2. For the other one, this is J3 I1. Let me write in all the other values. So we have 5, J2, J6 minus J4, and this is 100 with an amplitude, with a phase of 60. So now I can just apply KVL. Is that a question? All good? Okay. So let's do KVL for the first mesh and for the second mesh. So for the first mesh, I have minus 100 phase of 60 plus these two impedances times I1 minus this voltage source, which is J3 I1 minus I2. And then I have these two components to think about. These two will have a current flowing through them of I1 minus I2. So this will be current flowing this direction. So I need to define the polarity of this inductor, which is from top to bottom. So this will be plus J6 I1 minus I2 minus J3 I1 equals 0. So yeah, it gets quite complicated, and it helps a lot to have those equivalent sources in so we don't miss anything. My second equation, fortunately this is going to be a bit simpler. I'm just looking at this second mesh here. So I can see that J4 is only impacted by I2. I have this voltage source, J3 I1, and I have the current now flowing into this negative terminal. So this is negative J6 I1 minus I2 equals 0. If I was to simplify this second KVL equation, I would get minus 4 plus 6, so this is plus J2 I2, and then I have 3 minus 6, so this is minus J3 I1. So the current we are interested in is the current across the capacitor, so this is I2. So like last time, I'm going to prioritize trying to find I2. So first things first, I1 is going to be 2 on 3 I2, and then I can sub that into my first equation to find I2. So this will be, so if I use both of these, I will get minus 100, 60 degrees, plus 5 plus J2. I1 is 2 on 3 I2 minus J3, 2 on 3 I2 minus I2 plus J6, 2 on 3 I2 minus I2 minus J3 I1. Sorry. This is also ELEC2134 I2. And if I solve this equation, I get I2 equals 26.83 with a phase of 86.6 degrees amps. Cool. And that is our final answer. Any questions about magnetically coupled circuits? Cool. All right, well, that's all the content. If you guys want to stick around, or are people waiting outside to use this? Okay. We're out of time. Hope you guys enjoyed the crash course. Thank you all for coming, and good luck with your midterm next week. All right, thanks guys. Cool. All right, let's wrap up.